Hello everyone. In this lecture, I am going to explain about computation of eigenvalues and eigenvectors. Let's see one problem. Compute the eigenvalues and corresponding eigenvectors of A equals to 1, 0, minus 1, 1, 2, 1, 2, 2, 3. So the definition of eigenvalues, the roots of the characteristic equations are called eigenvalues. Coming to eigenvector, let A be a square matrix, a non-zero vector, X is said to be a eigenvector of A if there exists a scalar lambda such that Ax is equals to lambda x. So A must be a square matrix. There exists a non-zero vector x is said to be an eigenvector of A if there exists a scalar lambda such that Ax is equals to lambda x. So this we can write as A minus lambda of x equals to null matrix. The solution of this homogeneous system gives eigenvector. So for this, for eigenvalues, first write matrix A minus lambda I. The matrix A minus lambda I equals to A is 1, 0, minus 1, 1, 2, 1, 2, 2, 3 minus lambda into identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1 equals to 1 minus lambda. Subtraction of these two matrices, the resultant matrix is 1 minus lambda, 0, minus 1, 1, 2 minus lambda, 1, 2, 2, 3 minus lambda. So now I am writing characteristic equation of A, that is determinant of A minus lambda equals to 0. So determinant of, we know A minus lambda matrix, right? So 1 minus lambda, 0, minus 1, 1, 2 minus lambda, 1, 2, 2, 3 minus lambda equals to 0. So simplifying this, we'll get characteristic equation, that is lambda cube minus 6 lambda square plus 11 lambda minus 6 equals to 0. So calculating the roots by using trial and error, we'll get 3 roots. Lambda is equals to 1, 2 and 3. These are the eigenvalues of A. Now we have to compute eigenvectors corresponding to the eigenvalues. Lambda is equals to 1, 2 and 3. So the eigenvector corresponding to the eigenvalue lambda equals to 1. So let x equals to x, y, z be an eigenvector corresponding to the eigenvalue lambda equals to 1. Right? So x is the eigenvector, means then A minus lambda of x equals to null matrix. So what is our lambda value? Lambda equals to 1. So the system is 1 minus 1, 0, minus 1, 1, 2 minus 1, 1, 2, 2, 3 minus 1. X is x, y, z equals to 0, 0, 0. Now simply subtract the diagonal elements of subtract 1 from diagonal elements of A. So 1 minus 1, 0, 0 minus 1, 1, 1, 2, 2, x, y, z equals to 0, 0, 0. So the solution of this homogeneous system gives eigenvector. So for that, convert the coefficient matrix to echelon form. So apply the operations, row operations, R1 to R2 and R2 to R1. So this gives so 1, 1, 0, 0 minus 1, 2, 2, x, y, z equals to 0, 0. In second row we have 2 zeros. So to convert echelon form, third row minimum 3 zeros. So first make this element 2 as 0, R3 implies R3 minus 2 R1. So first row is not changed, 1, 1, 0. Second row also 0, 0 minus 1. Third row is R3 minus 2 R1. So 2 minus 2, 0, 2 minus 2, 0, 2 minus 2, 0. Now 1 1 0 0 minus 1 0 0 xyz equals to 0 0. So we can write this system as 1 time of x 1 into x plus 1 into y plus 1 into z. So x plus y plus z equals to 0. 0 into x plus 0 into y minus 1 into z equals to 0. So minus z equals to 0. So this implies z equals to 0. When z equals to 0, this equation gives x plus y equals to 0. So the rank of the quotient matrix is 2. We have two non-zero rows. So rank is 2. We have to assign arbitrary values for n minus r variables. N is number of unknowns. So here number of unknowns are 3 and r is nothing but rank. Rank of quotient matrix, that is 2. So assign arbitrary values for n minus r equals to 3 minus 2 equals to 1 variable. Now I am assigning arbitrary value for one variable. So let's say y equals to k. So choose y is equals to k. Then x value is minus k. Now we know the values of x, y and z. So our eigenvector is x, y, z equals to x equals to minus k, y equals to k, z equals to 0. So minus k, 0 is the eigenvector corresponding to eigenvalue lambda equals to 1. So similarly, the eigenvector corresponding to the eigenvalue lambda equals to 2. So subtract 2 from diagonal elements of A. So we will get 1 minus 2, 0 minus 1, 1, 2 minus 2, 1, 2, 2, 3 minus 2, x, y, z equals to 0, 0. So minus 1, 0 minus 1, 1, 0, 1, 2, 2, 1, x, y, z equals to null matrix, 0, 0, 1. Now convert the coefficient matrix to echelon form. So R2 implies R2 plus R1, R3 implies R3 plus 2R1. So that is minus 1, 0 minus 1, 0, 0, 0, 2 minus 1, x, y, z equals to 0, 0. In echelon form, 0 rows must be below of non-zero rows. So again, interchanging the rows, R2 to R3, R3 to R2. So R1 is not changed, minus 1, 0 minus 1, R2 to R3. So 0 to 0, 2 minus 1, and again R3 to R2, 0, 0. X, y, z equals to 0, 0. So write the equation form, minus 1 into x minus z equals to 0. 2y minus z equals to 0. Here also rank is 2. So we have to assign arbitrary values for n minus r equals to 3 minus 2 equals to 1 variable. So assign arbitrary value for any one variable. So assign z equals to k. You can assign x equals to k also. So choose z equals to k, then x value is minus k and y equals to k by 2. So now the eigenvector is x, y, z equals to x equals to minus k and y equals to k by 2, z equals to k. So minus k, k by 2, k is the eigenvector corresponding to eigenvalue lambda equals to 2. The eigenvector corresponding to eigenvalue lambda equals to 3. So this is also same. 1 minus 3, 0 minus 1, 1, 2 minus 3, 1, 2, 2, 3 minus 3, x, y, z equals to 0, 0. So that is minus 2, 0 minus 1, 1 minus 1, 2, 2, 0, x, y, z equals to 0, 0. So interchanging the rows R1 to R2 and R2 to R1, 1 minus 1, 1, minus 2, 0 minus 1, 2, 2, 0, x, y, z equals to 0, 0. So now convert this matrix into echelon form. R2 implies 2R1. First make this element minus 2 as 0. So R2 implies 2R1 plus R2. So now, and R3 implies R3 minus 2R1. So this gives 1 minus 1 1, 0 minus 2 1, 0 4 minus 2, xyz equals to 0 0. The second row we have 1 0. So that means in the next row minimum 2 zeros. So for that apply this operation, R3 implies R3 plus 2 R2. So 1 minus 1 1, 0 minus 2 1, 0 0, xyz equals to 0 0. So x minus y plus z equals to 0, minus 2y plus z equals to 0. So rank is 2. Again we have to assign arbitrary value for one variable. Choose z equals to k, then x equals to minus k by 2 and y is equals to k by 2. So the eigenvector is xyz equals to 1 minus 1 minus 2. So now the eigenvectors corresponding to eigenvalue lambda equals to 1 comma 2 comma 3 are x1 equals to minus 1 1 0. Second eigenvector is minus 2 1 0. Third eigenvector is 1 minus 1 minus 2. So this is the computation of eigenvalues and eigenvectors. Now we see algebraic and geometric multiplicity. So algebraic multiplicity of eigenvalue of A is the number of times lambda appears as a root of the characteristic equation. The meaning is how many times the eigenvalue is repeated. So in our example, previous example, the eigenvalues are 1, 2 and 3. So how many algebraic multiplicity of 1 is the number of times the eigenvalue is repeating. So only one time. So algebraic multiplicity of eigenvalue 1 is 1. Algebraic multiplicity of eigenvalue 2 is also 1. Algebraic multiplicity eigenvalue 3 is also 1. So similarly we calculate geometric multiplicity. Geometric multiplicity of an eigenvalue lambda is the number of linearly independent eigenvectors corresponding to the eigenvalue lambda. Geometric multiplicity of an eigenvalue lambda is the number of linearly independent eigenvectors corresponding to the eigenvalue lambda. So number of linearly independent eigenvectors corresponding to the eigenvalue lambda is n minus r. So n is number of unknowns, rank is r is rank. Note: geometric multiplicity is not greater than algebraic multiplicity.